Jai Hind everyone. Today we are going to discuss the very most popular terminologies that are Hive and Pig. So let me start with the Apache Hive. Whenever we thought about analytics, doing analytics, right? But analytics at a massive amount of data. We need to do a data analytics on a massive amount of data. Then the answer we have, that is a Apache Hive, right? So Apache Hive is a distributed fault tolerant data warehouse system that enables analytics at a massive scale, right? That's what I was talking about. Whenever we talk about analytics at a massive scale, right, then we have Apache Hive as a solution. Fine. It provides a central store of information that can easily be analyzed to make informed as well as data driven decisions, right? Hive allows users to either user want to read, other user want to write, and if that needs to manage massive amount of data, for example, say petabytes of data, using SQL-like interface. And what that SQL-like interface is known as in the Hive, that is known as HiveQL, Hive Query Language, right? It is moreover like SQL, as we are having a structured query language, and we all are aware, very much aware with that SQL, right? Hive is built on top of Apache Hadoop, which is an open source framework used to efficiently store and process large data sets. What is the Apache Hadoop? We have already discussed in our earlier lectures, very well understood that, and we have seen that where the Apache Hive is residing when we talk about the architecture, right? So as a result, we can say that Hive is closely integrated with Hadoop, fine, and is designed to work quickly on petabytes of data on a massive amount of data, right? What makes Hive unique is the ability to query large data sets, leveraging Apache Tej or MapReduce with SQL-like interface, right? So now I'm going to start with the Hive architecture. Before discussing each and every component of Hive architecture, let me show you the architecture itself. Here we can see on the top of the layer, on the top of the architecture, we have a upper layer that is a Hive, where what it is showing, we are having some drivers. As always, in any of the architecture, we must be having some drivers which are helping us to drive the whole thing. The compiler, the optimizer, executors are there, right? We are having a meta store, which is having the complete information of each and everything, of the documents, of the data, metadata about the data, data dictionary, statistics, command line interface, web interface, Thrift server, and yes, we have JDBC, ODBC server as well for connectivity. How it is working, we'll see one by one, each and every component. The Hadoop, which is a MapReduce plus SDFS, which we have already discussed in detail, and the job tracker, name nodes are there, right? Data nodes and task trackers are also there. That means some of the, you can say a master slave architecture is working. The name nodes are there, which is assigning some data to the, which is assigning some tasks to the data nodes. The data nodes are, we can say, these are the slave nodes, which exactly performing that particular job, right? The job tracker similarly is assigning some tasks to the task trackers, right? So how it is working, we'll see. Now I'll be discussing all the components one by one in detail. So first of all, we say UI. What is a UI? UI is a user interface. What is a user interface? The user interface for users to submit queries to the system, right? As we all are aware, how a user can interact with the system. Fine. It has been assigned a interface through which we used to interact with the system, right? When we say interaction with the system, what does it mean? That means in any of the form, we need to provide some input. That input needs to be processed, and then we will be getting some output, right? For example, in your mobile phone, you are touching any application, then it is getting opened. When it is opened, we are getting a home page. What is that home page? We are providing some information, and then we are able to access the system, maybe a database or something like that. That means that is an interface through which we are interacting, right? Driver is the component which receives the submitted queries. I have provided some say university roll number, and then I have clicked on submit button. Fine. In that case, a query will be fired. Okay, select so and so data from so and so table. In general, right? In the same manner, we are providing some input, right? So the component which receives the submitted queries, this component implements the notion of sessions, handles and provides, executes and fetch APIs modeled on JDBC ODBC interfaces, right? Next we have, that is a compiler. The component that parses the query does semantic analysis on the different query blocks and query expressions, and eventually generates an execution plan with the help of the table and partition metadata looked up from the meta store, right? Now the question arises, what is a meta store? As we have seen, this is a component which store all the structure information of various tables and partitions in the warehouse, including either the column and what is the type of the column, that information as well it stores, right? And the serializers, deserializers, which are necessary to read and write data, and the corresponding SGFS files where the data is stored, right? That's why we are calling it as a meta store. As the name is indicating, it is storing all the information, right? The component which is storing the information related to structure of the various tables, the partitions in the warehouse, whether it is in whether we are talking about the columns and the column type information, serializer, deserializers, which are necessary to read and write data, corresponding SGFS file where the data is stored, and everything, right? Then we have execution engine. What this execution engine is doing? This is the component which executes the execution plan created by the compiler. In the previous slide, we have seen the compiler, that is the component which parses the query, does the analysis on the different query and query blocks and the expression, and also it is generating the execution plan, right? Now, execution engine is there. Execution engine is there, which will execute the execution plan created by the compiler. Fine. The execution engine manages the dependencies between these different stages of the plan and executes these stages on the appropriate system components. It needs to find out what is the appropriate system component for this execution plan, right? And at a particular stage. So that is about the Hive architecture. Now we see what are the different ways to access Hive. Number one, Hive command line interface, right? Second, we have web interface, the Hive web interface. Next, we have server. Here it is a Hive server. Then JDBC, ODBC. So what are these? Hive data model, right? So, how the data in Hive is organized? The data in Hive is organized into some tables, some partitions, buckets. So, how it is working? We'll see one by one. What does it mean by a table? These are analogous to tables in the relational database, right? As we have already discussed about RDBMS properly in the unit 2. So, I'll continue with the partitions. Partitions, or also we can say directory. What does it mean? What a directory is having? It is having the complete information about the system, right? So, in the case of partitions, each table can have one or more partition keys. One or more partition keys which determine how the data is stored. When we are creating the partitions, a partition key needs to be created so that we can connect, we can establish a relation, or we can link between the tables, right? For example, a table T with the date partition column DS had files with the data for a particular date stored in the whatever the table location is there, and DS equals to date, right? We have taken a date partition, so it is equals to date directory in SDFS, right? Next, we have buckets. Buckets also we can say, or also we can understand in terms of files, right? Partitions can be understood in terms of directory, which is having the information related to the table and all, and the partitions and so on. Buckets can be understood in the terms of files. So, what is a file? What is a bucket? Data in each partition may in turn be divided into few of the buckets. Where it depends, on which it depends? It depends on, it is based on the hash of a column in the table. Each bucket is stored as a file, right? That's what I told you, that we can understand the buckets in terms of files. Each and every bucket that is stored as a file in the partition directory, right? More precisely, how we can understand the bucketing and partitioning? One can use one column to partition data, right? Each partition stored in a separate file. Partitions, as I told you in the previous slide, we can understood in the terms of directory. Buckets could be understood in terms of files, right? So, can use one column to partition data. Each partition stored in a separate file. For example, if I am creating a partitions on the basis of country, I am having a data of some employees and say some customer or some person, and now the data needs to be partitioned based on the base of some of the column. For example, here I have taken country. No difference in syntax, but querying on partitioned attribute is fast, right? Okay, that was about partitioning of data. Now, can cluster data by buckets. What does it mean by a cluster? Clustering simply says that we can create a group of the related data, right? Can cluster data by buckets, randomly hash data into buckets. What it does? It allows parallelization in MapReduce, right? Which helps in parallelization in MapReduce. That means one mapper per bucket we have assigned, okay? Use buckets to evaluate queries on a sample. We can use buckets to do a evaluation of a query on a sample. Here, we can take one bucket, right? So, that's how bucketing and partitioning is working in Hive. Fine. So, as a summary, we can say bucketing is another method of partitioning. right? Partitions are basically the directories, whereas bucket is a file, right? So that was about Hive and Hive architecture and its components. Now we will be discussing about pig, what the pig is. So here I'm going to discuss the pig introduction and the pig architecture. So let me start with the introduction to Apache pig, right? We have a great discussion on MapReduce in the previous lectures. When we use the term Apache pig, what does that mean? Pig is an abstraction over MapReduce. What does it mean? It says that is a tool, or we can say it is a platform which is used to analyze larger sets of data, representing them as data flows. Pig is generally used with Hadoop. It can perform all the data manipulation operations in Hadoop using Apache pig, right? To write data analysis program, pig provides a high-level language which is known as pig Latin. As we have seen in the case of Hive, we have HiveQL, Hive query language, right? And here in the case of pig, it provides a high-level language which is known as pig Latin, right? What this language is providing us? It is providing us various operators which programmers can develop their own functions for reading, for writing and processing of data, right? To analyze data using Apache pig, programmers need to write scripts. Here, the programmers are not writing the queries in any of the query language, like we have seen SQL in RDBMS, we have seen HiveQL in the case of Hive. No, there are not queries, there are scripts, right? And in which language those scripts will be written? There is a pig Latin language. In the pig Latin language, the pig scripts will be written, right? Now, how these scripts are being processed and executed? All these scripts are internally converted to map and reduce task, right? Apache pig has a component which is known as pig engine. Likewise, we have seen query evaluation engine in the case of SQL, in the case of HiveQL, right? Here we have pig engine which accepts the pig Latin scripts which has been written in the language, that is pig Latin, and those scripts will be accepted by the pig engine and processing will be done, that will be converted into map reduce jobs, right? I repeat, pig engine accepts the pig Latin scripts as input and converts those scripts into the map reduce jobs. This is the Apache pig architecture here, where we are having the pig Latin scripts. As we have seen in the previous slides, there is a pig Latin language in which programmers are required to write the scripts, right? Then we have the complete architecture of the pig, Apache pig. Here the grunt shell for handling the scripts, the pig server is there. Now the complete processing related to the compiler will be taking part, compilation and execution. A parser is there, optimizer is there, compiler is there, and execution engine is there. That's how that those scripts will be evaluated and processed, and then that will be converted to map reduce jobs, right? That will be converted to map reduce jobs. And here we can see Hadoop component is there, right? So Now we can easily see, we can easily understand that pig architecture consists of pigletten interpreter and it will be executed on the client machine, right? It uses pigletten scripts and it converts the scripts into a series of MapReduce jobs, right? That's what we have seen in the previous slide. Then it will execute MR jobs and saves the output results into HDFS. Let me show you the architecture again that has been converted into MapReduce jobs and will be stored into HDFS, right? The output results into HDFS. In between, it performs different operations like which operations we have seen in the architecture: parsing, optimization, you can say, compilation and execution engines are there, right? So in between it performs different operations like parsing, compilation, optimizing, and the execution on data that comes into the system, right? So that these are the components of the pig architecture. First one, parser, as we have discussed many number of times in multiple terminologies. The main functionality, again, that is the same what a parser used to do. Initially, the pig scripts are handled by the parser. It checks the syntax for the scripts, does type checking and other miscellaneous checks. The output of the parser will be a DAG, directed acyclic graph, which represents the pigletten statements and the logical operators if these are in our script, right? In the DAG, or we can say the directed acyclic graph, the logical operators of the scripts are represented by the nodes and the data flow from source to destination, that is represented as the edges, right? Next we have optimizer. The logical plan, or what is a logical plan? That directed acyclic graph, that is passed to the logical optimizer, which carries out the logical optimization, for example, projections and the push down. Next we have compiler. The compiler compiles the optimized logical plan into a series of MapReduce jobs, right? That's what we have seen in the pig architecture. Then execution engine is there. Finally, the MapReduce jobs are submitted to Hadoop in unsorted order, and these MapReduce jobs are executed on Hadoop, producing the desired result, right? So how the job execution flow is going on? When a Apache Pig programmer develops scripts, they are stored in the local file system in the form of user-defined function, right? When we submit a pig script, it comes into the contact with pigletten compiler, which splits the task and run a series of MapReduce jobs. Meanwhile, pig compiler fetches data from HDFS, that is the input file present. After running MapReduce jobs, the output file is stored in HDFS. Fine. Now the question arises, why do we require Apache Pig? What is the requirement of using Apache Pig? Multiple advantages or multiple benefits are there. Some of them are programmers who are not so good at Java, normally used to struggle working with Hadoop, especially while performing any MapReduce task. Apache Pig is a boon for all such programmer. Whosoever is having a fear of using Java programming language, they can simply use Apache Pig, because there are the very simple scripts are there that needs to be written by the programmer, and we have Latin language for that, pigletten language for that. So we can say using pigletten language, programmers can perform MapReduce tasks easily without having to type a complex code in Java. It uses multi-query approach. What is that? Thereby reducing the length of the code. For example, it is very important to understand an operation that would require you to type 200 lines of code, 200 LOC we can say in Java, but can easily be done by typing as less as just 10 line of code in Apache Pig. That's how we can understand very easily how simple the Pig is as compared to Java. Pig scripts are as compared to Java. Where in the Java, when we was having a need to write 200 lines of code, here we can do with the help of just 10 line of code, right? So ultimately, Apache Pig reduces the development time by almost 16 times, right? So that is a very important, you can say, a difference or a benefit of using Apache Pig. Pigletten is SQL-like language, and it is easy to learn Apache Pig when you are familiar with the SQL. Apache Pig provides many built-in operators to support data operations like joins, filters, ordering, and so on. Also, it provides nested data types like tuples, bags, maps that are missing from the MapReduce. So that was the data model for which I was talking about. Here we have 4 simple data types. One is atom, tuple, bag, and map. Atom, these are the simple atomic values like the string or numbers. Tuple, sequence of fields of any type of data. Then we have bag, a collection of tuples with possible duplicates. Then map, which is a collection of data items with then associated keys, always an atom, right? So this is an example of a data model in Pig, right? How what the bag is, what a tuple is, what is a field, right? So, and these are few of the operators, working with the operators in the Pig, like for each, assert, filter, group, group by, distinct, join, limit, sample, split. These are almost the same operators as we have discussed in SQL. Similarly, it works. So now we'll see what is the main difference in Apache Pig and Hive, right? So differences between the Pig and Hive, it depends on the purpose and the type of the data. You can either choose to use Hive Hadoop component or Pig Hadoop component, which is based on the below difference. What is the difference? Hive Hadoop component is used mainly by data analysts, right? Whereas Pig Hadoop component is generally used by the researchers and the programmers. That is the main difference in the Pig and the Hive, right? Apart from multiple differences, that is the main difference, right? Okay, so that was about Hive and Pig, which we have discussed. And here, these are the references from where I've included the contents in my slides. Thank you.